The universe began billions of years ago from an extremely hot, dense state and has been expanding ever since. It remains one of the most influential frameworks for understanding the universe's origin. Yet, the new observations being collected and analyzed are forcing scientists to revisit some of its core assumptions. One major focus of this ongoing discussion is the age of the universe and the rate at which it is expanding, two elements that are critical to our overall model of how the cosmos operates. For years, scientists have relied on a value known as the Hubble constant, a measure of the universe's expansion rate, to determine both the size and age of the universe. But calculating this constant has proven far more complex than originally thought. There are two primary methods used to estimate the Hubble constant. And unfortunately, the results derived from these methods don't align. This discrepancy has led to one of the most intriguing puzzles in modern astrophysics. The first method is based on local measurements. This approach uses what astronomers refer to as standard candles, astronomical objects like Cepheid variable stars and Type Ia supernovae that have a known intrinsic brightness. By comparing their observed brightness to their known luminosity, astronomers can determine how far away they are. Then by measuring how fast these objects are moving away from us, scientists can calculate the Hubble constant. These local measurements suggest that the universe is expanding faster than previously believed. The second method involves observations from the early universe. Scientists analyze the cosmic microwave background, or CMB, which is the afterglow of the Big Bang. This radiation has been traveling through space since the universe was only about 380,000 years old. Discovered in the 1960s, the CMB has been instrumental in shaping our understanding of the early cosmos. By examining the minute fluctuations in temperature and polarization within this radiation, cosmologists can infer the universe's age and rate of expansion at that time. However, there's a serious issue, one that has only grown more pressing. The results from local measurements and those from the CMB do not match. This discrepancy is known as the Hubble tension, and it's become one of the most significant unsolved problems in astrophysics today. If both measurement methods are valid, and there's reason to believe they are, it suggests that there is a fundamental aspect of the universe we are missing or misunderstanding. Scientists have worked tirelessly to determine whether the disagreement stems from observational errors, misinterpretations, or a deeper issue within our theoretical framework. This is where the James Webb Space Telescope enters the picture. With its advanced infrared capabilities and its ability to observe distant objects with unmatched clarity, the telescope allows us to peer further into the universe than ever before. Scientists hoped its data would help reconcile the conflicting measurements and refine our understanding of the Hubble constant. But instead, the first wave of data from Webb has only deepened the mystery. The results continue to diverge from what was expected based on previous models, suggesting that our understanding of cosmic expansion may require a fundamental overhaul. Rather than closing the gap between the CMB measurements and the local observations, Webb's insights are widening it. These findings are prompting scientists to think beyond established theories. The discrepancies might point toward new physics, undiscovered particles, or forces that could reshape our understanding of space and time. They may also indicate that our current model of dark energy, the mysterious force believed to be accelerating the expansion of the universe, needs to be reconsidered. Every time we uncover new data, it pushes the boundaries of what we know and forces us to reassess our theories. Take, for example, the discovery of the cosmic microwave background in 1965, which provided compelling evidence for the Big Bang theory. Before that discovery, many scientists believed the universe would continue expanding forever at a steady rate. However, the observation of accelerated expansion in the late 1990s introduced the concept of dark energy, a force that acts in opposition to gravity and causes the universe to expand faster over time. This was a major turning point, demonstrating that even the most trusted theories must adapt when faced with new evidence. Today, scientists are dealing with similar challenges. Each discovery raises new questions and forces a comparison with previous knowledge. The process may be complex, full of uncertainty and revision, but it is also incredibly rewarding. Confronting problems like the Hubble tension compels researchers to develop better tools, refine their methods, and explore new ideas about the universe's past, present, and future. The questions surrounding the Hubble constant aren't just abstract puzzles. They influence everything from how we model galaxies to how we predict the ultimate fate of the cosmos. Another crucial concept closely tied to the Hubble tension is what scientists refer to as sigma tension. This deals with how matter is distributed throughout the universe. When astronomers observe space, they see that galaxies aren't spread out evenly. Some regions are packed with galaxy clusters while others are nearly empty. Understanding why this is the case can help us trace the universe's evolution over billions of years. To investigate this, scientists use a technique called gravitational lensing. This occurs when massive objects like galaxy clusters bend the light from even more distant galaxies behind them. This bending effect helps astronomers detect dark matter, an invisible form of matter that doesn't emit or absorb light. It reveals itself only through its gravitational pull. Gravitational lensing gives scientists a way to map the distribution of dark matter across the universe. They also turn again to the CMB, which contains information about the earliest fluctuations in matter after the Big Bang. However, a new problem has emerged here too. The irregularities predicted by studying the CMB do not match the large-scale structures observed in the present-day universe. In particular, the gravitational patterns we see now suggest that matter was less evenly distributed in the early universe than the CMB data implies. This inconsistency again points toward the possibility that there's something missing in our current understanding. Perhaps it's something about the behavior or nature of dark matter that we have yet to grasp. A research team led by Adam Rees explored whether the differences in measurements could be attributed to errors in the Hubble Space Telescope's data. But when they used the James Webb Space Telescope to check, they saw the same inconsistencies. This raises an even more concerning possibility, that there is a fundamental flaw in how we interpret cosmic observations. In an interview with an American astronomical journal, Rees remarked that somewhere between these two methods, local and early universe measurements, there may lie a key misunderstanding that needs to be uncovered. Thanks to the James Webb Telescope's precise infrared imaging, researchers are now able to observe objects at much greater distances with improved accuracy. These capabilities help refine the measurement of cosmic distances and further highlight the discrepancies between various methods. But the new clarity has not brought harmony to the data. It has only made the contradictions clearer. Instead of convergence, we're seeing sharper divergence. As the James Webb Space Telescope, JWST, continues to gaze deeper into the fabric of space-time, it does more than collect data, it challenges our assumptions. One of the telescope's most powerful contributions has been in expanding our reach, not just in distance, but in time. Every photon it receives from galaxies billions of light-years away is a message from the distant past, a fragment of the universe's earliest chapters. In decoding this light, scientists are learning that the cosmos might not have unfolded according to our most cherished models. What was once thought of as a smooth, consistent expansion from a singular event, the Big Bang, is increasingly being viewed as a process far more chaotic, layered, and perhaps even cyclic in nature. Some of the most profound implications come from JWST's observations of distant galaxies that appear too mature for their cosmic age. These galaxies are too massive, too structured, and too chemically enriched to fit within the current timeline of galaxy formation. This has led some researchers to question whether the universe really began in a singular explosion 13.8 billion years ago, or whether that model oversimplifies a far more complex reality. Alternative theories, such as the bounce model, where the universe expands and contracts in cycles, or eternal inflation, which posits countless pocket universes within a multiverse, are gaining renewed attention. These are no longer fringe ideas, but legitimate considerations within the growing uncertainty of cosmological science. Further complicating the picture is the strange behavior of gravity on cosmological scales. While Einstein's general relativity has been successful in explaining the motion of planets and even the warping of space around black holes, it struggles to account for the observed distribution of mass and energy in the universe without invoking invisible substances, namely dark matter and dark energy. But what if the failure isn't with matter, but with gravity itself? Modified theories like gravity or scalar tensor models attempt to tweak the equations of general relativity to better match observations without needing to invent unseen particles. JWST could be instrumental in evaluating these models by mapping how galaxies cluster and how light bends around massive structures. One particularly promising avenue involves looking at the cosmic web, the vast network of filaments, clusters, and voids that comprise the large-scale structure of the universe. JWST's deep field imaging capabilities are revealing this web with unprecedented